Welcome to this lecture. Let's first recall what we have done so far. So in the previous lecture we had considered how to look at sizes of sets in a sigma field, and the motivation was that this will help us understand which events are more likely to occur or which sets in a sigma field are more important, and this we are checking by the associated numerical value, and if the value is larger then we will say something is more important or more likely to happen than the other. So with this way or with this motivation, what we did, we defined something called set functions, and then we understood that for disjoint sets, pairwise disjoint sets, we should be able to add up the sizes, and with that motivation we looked at the special class of set functions which we called as measures. So what were measures? Measures were non-negative countably additive set functions on sigma fields. But then we clarified that these measures may take the value plus infinity. Alright, and with that we made this very specific assumption that there is a set with finite mass or finite size, and that allows us to prove that measure of empty set is 0, and using that we had proved the finite additivity of the measures and obtained certain other basic estimates involving the measures of sets or the sizes of sets. So with that in mind, we now start over and move on to the slides for this lecture. So in the previous lectures, these notions of measures and measure spaces were discussed. Now let's recall this important property that we proved almost at the end of the last lecture. So this was this fact that if mu is a measure on a measurable space, then you pick up any set from your sigma field, look at the size of that. So mu of A is the size of that set according to that set function way of measuring. So that is dominated from above by the size or mu of whole omega. Alright, so omega is the whole set. So what it says is that the maximum value achieved by this function mu is achieved at the whole set, and this is the maximum possible value. Okay, and with this in mind, we are now going to look at the special subclass of finite measures. So just to recall, we had looked at these two specific subclasses of measures. One was the case when mu of omega, the size of omega, was infinite, we called it an infinite measure, and the other one where mu of omega, the size of omega, was finite, and we called it a finite measure. So we are now going to look at this special subclass of finite measures, and this allows us to make this next definition. So what is this? So we define that a measure mu is a probability measure if mu of omega is 1. So we are looking at again the size of the whole set according to the set function mu, according to the measure mu, and we are saying that if mu of omega is equal to 1, then we are going to say that mu is a probability measure on omega script f, that measurable space. Now as we have seen earlier, when you have a measure on a measurable space omega f, then you can consider the triple. So take all these three things together, you get a triple, and we called it a measure space earlier. But now if it so happens that mu is a probability measure, then we shall refer to this triple, this measure space, as a probability space, and we are going to work on this kind of triples, this kind of probability spaces throughout the course. So again, if mu is a measure with the fact that mu of omega equals to 1, then we are going to call it a probability measure, and we are going to look at the corresponding triple, corresponding measure space, and also refer to it as a probability space. Now as soon as we make the definition, it's a good idea to look at some basic examples, and to do that, the first example, and this is a very important example in fact, as we shall find out, is called the Dirac measure on the real line. So again, just to recall the terminology that was introduced in the previous lecture. So we will call that a measure is on a measurable space. As long as the sigma fields are understood, we can as well say that the measure is on the domain omega, or equivalently we can also refer to the sigma field. So measure is actually defined on the sigma field, so we can also refer to it as that measure on the corresponding sigma field script f. So on the real line, most often we are going to work with the Borel sigma field. So if it is not stated, always assume that the Borel sigma field is taken on the real line. So when you are considering the real line, if the sigma field is not clearly stated, please consider the Borel sigma field. Now what we do, we are going to define a set function which we write it as this delta subscript small x. So we are going to fix this real number small x first and going to look at the corresponding set function which we are going to define now. So this is delta subscript x. So this is going to be a set function that is defined on this measurable space. So in fact it's a set function defined on the Borel sigma field. So how do you define this? It's pretty simple. So the point small x is fixed for you a priori, and then you vary your Borel sets capital A over the Borel sigma field. So now you are going to check this whether your point small x is in the set or not. If the point x is there in your set, then I assign the value 1. We say yes, the point is there in the set. Otherwise we assign the value 0. So this is simply a 0 1 valued set function. Okay. So therefore it's also a non-negative set function by definition. Correct. So it just takes value 0 or 1. Now this is pretty simple looking set function, but it turns out this actually happens to be countably additive, and therefore it becomes a measure on the Borel sigma field on the real line. So therefore this is a very important example of a measure which simply checks whether the parameterized point, that small x, is in the arbitrary set capital A or not. If it is there, then you put 1, otherwise it is 0. Alright. So please check that this set function is countably additive, and that will imply that it's a measure. So this is left as an exercise for you. Please check this. But as soon as it becomes a measure, you can now try to look at the size of the whole set, which is the real line here. So once you look at the size of the whole set, all you have to do is follow the definition. Is the point x in the real line? Yes, the answer is yes, because x was chosen like that. So therefore the answer to this value is 1. So therefore this becomes an example of a probability measure. So as soon as a measure is with the property that the measure of the whole set is 1, then it automatically becomes a probability measure as per our definition earlier. So therefore you have a very nice example of a probability measure on the real line. We are going to refer to this measure as the Dirac measure supported at the point small x. Dirac subscript x or delta subscript x. So that is the Dirac measure supported at small x. Now in an analogous fashion, you can actually extend these notions of Dirac measures on general measurable spaces. How? So all you have to do is that start with some non-empty set omega, take a sigma field script f, then for any fixed small x in your domain, look at this set function Dirac or the delta subscript x. For any arbitrary set coming from the sigma field, you just check whether the point small x is in the set A or not. If it is there, you assign the value 1, otherwise 0, exactly as done before. And it will happen that Dirac subscript x or delta subscript x, that's the Dirac measure, it will turn out to be a probability measure. So again, please check that this is countable additive and the size of the whole set omega now is also 1. Okay, please check this. So this is left as an exercise for you. Please check this. So the notion of Dirac measures can be extended to arbitrary measurable spaces, but most often we are going to restrict our attention to the real line as defined earlier. Okay, so this is on the real line. So we are going to look at this kind of structures throughout the course. All right. Now with this example at hand, one concrete example at hand, we are now going to look at certain properties of these probability measures, which will now allow us to construct more examples. So once you have some explicit examples at hand, like the Dirac measure, you can now use certain properties of probability measures, mix them up and construct more examples. So to do that, we state two propositions. So the first proposition says that you take a finite measure first. You take a finite measure, call it mu. So this is defined on this measurable space omega script f. Consider the set function. This we are now calling as nu. So originally the measure was mu, which was a finite measure. Now I am calling the new set function that I am going to define as nu. So how it is going to be defined? So it's still defined on the same sigma field that I have started off with, but then I am going to look at the values of the sets or the sizes of the sets according to the new measure defined like this. So what do? We look at the size of the arbitrary set capital A with respect to the original measure mu and divide it by the total measure of omega. Okay. So here we automatically have to assume that mu of omega is strictly greater than 0, otherwise this division is not well defined. So we are not allowed to divide by 0. So for a finite measure, as we have started off with, we are going to assume that mu of omega is strictly positive, it's not 0, and we are going to divide or look at the ratio of the size of the set with respect to the whole set. Okay, so that's the ratio I am looking at, and automatically this value is less or equal to 1 because mu of A, the maximum value it can take is mu of omega itself, that we have proved earlier. Okay, so this ratio is falls between zeros and ones. So nu of A as defined actually takes values between zeros and ones. Okay, now all you have to check that this is a probability measure. So this is the claim of the proposition. So let's try to go through this. So by definition, this set function nu is non-negative. Why? Because mu, the original finite measure, that was non-negative, and you are dividing by this positive quantity mu of omega, so the ratio is of course non-negative. So that's not a problem. So the next thing that we need to check for is countable additivity. So that will allow us to say that nu is a measure. So how do we do this? So you choose ANs, a sequence of pairwise disjoint sets coming from the sigma field script f. Then you look at the summation that you want to check countable additivity. You look at the summation. So on your left hand side, I am just adding up the individual sizes according to the new measure. So put in the definition. So this 1 by measure of the whole set according to the mu measure comes out. So that's a common factor, comes out of the summation, and you just have to add up the individual sizes according to the mu measure. But since mu itself is a measure, this will have countable additivity, and that allows us to write this ratio that on the numerator I have mu of the whole union, countable union of ANs. So this is simply using the countable additivity of the measure mu. But then I am dividing the whole quantity by the measure of the whole set, and then immediately I can write it according to the definition in terms of the new measure. So according to nu, this is simply the nu of the complete union or the countable union AN. So therefore we have proved that nu is a countably additive non-negative set function, and as per the definition it becomes a measure. But then as per our proposition, we wanted to claim that this actually is a probability measure. So how do you show this? You look at the size of the whole set according to the new measure. So what is this? As per the definition, this is on the numerator, this you have to simply put that set itself, so that is mu of omega, but then you are dividing by mu of omega as per definition, and hence this ratio is exactly 1. Okay, so therefore this becomes a probability measure and completes the proof. So all we are saying, so let's go back. As soon as you have some examples of finite measures, divide the actual measure by this constant, and then immediately what you get is this ratio which falls between zeros and ones. This automatically becomes a probability measure. So therefore, as long as you have examples of finite measures, you immediately get examples of probability measures. Okay, so that's the first result that allows you to construct more examples, and we will immediately apply this to look at some interesting examples of probability measures. So the example is uniform measure on a finite set. What do? We have to first of all work with finite measures. So take a finite set omega, call the points as x1, x2, xn, and look at the power set sigma field on top of it, and look at the counting measure on this. So remember, this gives you an example of a finite measure because the whole set has finitely many elements, So therefore the mu of omega here is exactly equal to n, the number of elements, and that will be finite. So this is a finite measure. So for this finite measure you can now apply this previous proposition and look at this new measure as defined there. So what is this? This simply says look at nu of a for any arbitrary set, which is now any arbitrary subset of omega because you are looking at the power set. So what do? You look at mu of a divided by the mu of omega. So the size of omega you divide it by. Great. But since we are looking at the finite set omega, all its subsets are also finite, meaning all subsets are finite number of elements. Therefore, as per the definition of a counting measure, what you get in the numerator is simply number of elements in the set A divided by the total number of elements in the set omega. So you are just dividing that number and dividing it by n. Okay. And as per the proposition, this new measure must be a probability measure. Okay. So let's explicitly compute what happens. So here, if you look at more explicitly on this non-empty set omega, you are looking at all possible subsets. In particular, you can also look at singletons. So if x1, x2, xn's were the individual points that you have identified, then look at the singleton sets xi. So this set is a subset of omega, so we can look at the size of that according to the new measure. And what is the number of elements in this set? It's exactly 1. So therefore, according to the formula which we have just computed, this ratio turns out to be 1 by n. So for each singleton set you get the value 1 by n. And now this gives you the uniform measure because it distributes the whole mass. The total mass is 1. It distributes the total mass 1 into n equal chunks, which is 1 by n. So you distribute according to the number of elements. So if number of elements is n, you are just getting 1 by n weights for each of these points. Okay. So again, if you are having a doubleton set, meaning a set with 2 elements, you will get the size as 2 over n. So that's what the meaning of the uniform measure. Okay. So this is an explicit example of a probability measure which we have constructed out of a finite measure. Here the finite measure was the counting measure. Alright. But now this is the interesting way to look at this previous example. So we say that we can look at, or we can write the measure nu according to a formal summation like this. What is this? I am saying look at this summation from I equal to 1 to n, 1 by n Dirac xi, or delta subscript xi, Dirac supported at xi. So we have looked at the Dirac measures, and I am saying that I am going to look at this summation, this formal summation. Now you are going to ask, what is this formal summation? So this means that for all arbitrary sets capital A from your sigma field, which is the power set here, we are going to have that the nu of A is simply this summation. What is this? This is summation from I equal to 1 to n, 1 by n, that's the same fraction that was written earlier, then Dirac measure supported at xi acting on the set A. So we are looking at the size of the set, arbitrary set A, according to the individual Dirac masses, and we are just adding them up with this scaling factor 1 by n. Okay. So now this is exactly the same measure that was obtained earlier. Okay. So that is another way to write down the same equality. This is simply counting whether the point xi is in the set A or not. But then if you check it for all possible I, meaning if you check for all possible elements, you are just counting up the number of ones there. Dirac simply associates the value 1 if the point is there is in your set capital A or not. So therefore, if you are adding up this summation from I equal to 1 to n, you are just checking whether the points x1, x2, xn is in your set or not. And the number of ones is exactly the number of elements in the set, and therefore you exactly get back the ratio number of elements in the set A divided by n. So that is the motivation for looking at this kind of a summation, and formally we are going to write it as a nu as a linear combination like this with the weightage 1 by n to each of the Dirac masses, right? So this is an interesting way to represent the nu measure. But then this observation has been put in the form of an exercise. Please try to write it down please check that this equality holds as discussed now. But motivated by this example, by this exercise, we are now going to look at some kind of combinations of such Dirac masses or more general probability measures. What do? We look at two probability measures, call them mu1 and mu2. Both of them are defined on the same measurable space. Now fix a constant p between 0 and 1. So it could be 0, it could also be 1, or it could be a proper fraction between 0 and 1. Then we are now going to look at a convex combination like this. So for any arbitrary set capital A, we are going to look at nu of A defined as the convex combination of measure of A according to mu1 and measure of A according to mu2. But we are going to associate the weights p and 1 minus p. So this is a convex combination of weights. So we are choosing this weight p, we are fixing this parameter p and looking at this convex combination p and 1 minus p. So with that weights, we are going to look at the convex combination of the size of A according to mu1 and the size of A according to mu2. Look at this convex combination. Now that I am saying will give you a probability measure. So let's quickly check this out. So again, by definition, nu of A is non-negative. Why? Because p and 1 minus p both are non-negative. mu1 and mu2 are probability measures. So in particular, mu1 of A and mu2 of A both are non-negative. So therefore this combination that you are looking at is non-negative. So nu is a non-negative set function. So that's not a problem. But let's try to check the countable additivity. So how do you check this? Again, start with a sequence of pairwise disjoint sets in your sigma field. Then let's start with that right hand side of the countable additivity property, add up the individual sizes. So for the individual sizes, put in the definition. So this is simply will give you these two individual series, one for the mu1 and another for mu2, with the individual weights coming from the convex linear combination p and 1 minus p. So just put in the definition of the nu of an and you will immediately get this series on your right hand side. But then you observe that mu1 and mu2 are genuine probability measures. In particular, they are countably additive, and therefore you end up having that this is a convex linear combination of the measures of the union of ANs according to mu1 and mu2. So here you are simply using the countable additivity of mu1 and mu2. Therefore, all you get is the convex linear combination, and as per the definition, this is nothing but the nu of the countable union of ANs. So again, you have managed to prove that nu is countably additive, and hence this becomes a measure. But then our original claim was that this measure is in fact a probability measure. So how do you check this? All you have to check is the measure of the whole set. So we are going to look at the size of the whole set omega. So nu of omega, what is this? Put in the definition. So this is nothing but the convex linear combination of the size of the set omega according to mu1 and mu2, but with these weights p and 1 minus p. So that's the convex linear combination. Mu2 of omega is also 1 because this is a probability measure, and hence you end up with this formula. This is simply p plus 1 minus p, which is nothing but 1. So therefore, with this convex combination that you have looked at, this gives you total measure 1 for the set function nu. So for a convex combination of measures, you end up having a probability measure. So let's go back. So we are saying that take two probability measures mu1 and mu2 and look at these convex combinations of individual sizes, correct? And therefore we are ending up with a probability measure. So again, as mentioned a few minutes back, we are now going to remove this set capital A from this equality as defined here, and we are going to look at this formal summation as some kind of functional equation. So therefore we are going to write this as a convex combinations of p and 1 minus p. So those are the weights that appear in the convex combination, and it will be a convex combinations of the measures mu1 and mu2 with the weights p and 1 minus p. So that is the motivation that we have looked at. Now this was for convex combinations of two things, two measures mu1 and mu2, correct? Now we can do the extension of this result, and this is stated in exercise 3. So take n measures, n probability measures mu1 up to mu n all of these are defined on the same probability space omega script f. Now you are going to choose convex combinations, so you have to choose scalars alpha 1 up alpha 2 up to alpha n non-negative with the sum equal to 1. So this will be the weights for the convex combinations. Then what you are going to look at is this new measure given by these convex combinations alpha i's mu i's. Now you should be clear what this equality means. It simply means that if you want to compute nu of some arbitrary set A, all you have to do is to look at mu i's of A. So the size of the set A according to mu I, first compute that, then multiply by the weights alpha I and add them up. So that will be the convex combinations of the sizes of the sets A in terms of the individual measures mu 1 up to mu n. So then as per the exercise here, it will also be a probability measure. So this proof goes through exactly the same arguments as considered for the convex combinations of two probability measures. So the same argument goes through and you will get this. And this was in fact the special case that was mentioned earlier in exercise 3 as the motivation. So what we said was that the uniform measure on a finite set came out to be these convex combinations of the Dirac masses. So that's exactly what was our motivation for looking at such combinations, such convex combinations. Okay. But with that in hand, we can now identify that thing. So we can now connect these exercises 2 and 3, which was our motivation, that you just say that mu i's where this Dirac of xi's and alpha 1 up to alpha n is exactly 1 over n. So that's the convex combination that is given earlier. Okay. Now we can extend this exercise 3, which was for this finite combinations, to infinite combinations involving series. What you have to do? You now look at a sequence mu n of probability measures and the corresponding sequence of weights. So these should be non-negative and they should add up to 1. So you are now looking at series. Now the question is the set function nu given by this countable summation alpha n mu n a probability measure? And the answer will be yes. Please try to work this out. Again, the meaning is same. If you take a arbitrary set capital A, then all you have to look at is first mu n's of A, the weights of the set capital A according to mu n, and then multiply by alpha n and add them up. So that will give you a probability measure. Please check this. Now these exercises allow us to construct more examples. So how? We are now going to look at convex combinations of probability measures. Remember, the explicit example of probability measures that we have are the Dirac measures. Now on the real line, consider the Dirac measures Dirac 1 and Dirac 0, meaning the Dirac measures supported at 1 and Dirac measures supported at 0. If you choose an appropriate p between 0 and 1 and look at this convex linear combination as per the proposition 2 above, you can immediately get this probability measure. Okay, so let's go back. Yes, so this is the proposition 5. Sorry, the correction will be made. So this will be proposition 5. Sorry. So the proposition 5 will imply that probability of delta 1 and 1 minus p delta 0, that will be a probability measure. Okay. Now you apply exercise 3, which was for combinations of more than 2 measures. So again look at Dirac measures but support it at integers from 0 to n, and look at these combinations given from the binomial coefficients. So choose some p between 0 and 1, fix a positive integer n, look at these coefficients. These coefficients, as before, these are familiar coefficients, they add up to 1 as given by the binomial theorem. So these coefficients add up to 1 and this will give you a convex linear combination for you of the Dirac measures. And as per the exercise earlier, this will be a probability measure. Okay, so let's go back. So this is the exercise that I am referring to, that while you are looking at convex linear combinations of n measures, n probability measures. Okay, all right. But then we also looked at the series version of this, where you are looking at a sequence of probability measures. And as I already mentioned, that exercise 4, I left it as a question, but I mentioned that this answer to that is yes, you can get this as a probability measure. So then you look at these Dirac measures supported at the points k, at the integers k from 0 to infinity. So So look at all possible non-negative integers and look at these weights. So which is this? What is this? So this is exponential minus lambda power k by k factorial. So these weights, if you just look at them all alone, adding them up, you get 1. So this also denotes some convex linear combinations of these Dirac masses. So this will again be a probability measure. Now let's just go back and look at all these examples. So these examples that we have so far said from these exercises are following certain parameters. Here it was n and p, and here there is a parameter lambda which is taken to be positive. Then what will happen is that we are going to connect these explicit examples of probability measures with some known random variables, known discrete random variables. This we are going to see them later on when we start discussions about random variables. But these examples are coming simply from looking at the convex linear combinations of the Dirac masses. Okay. Now some final exercises to finish off the lecture. So earlier we had looked at convex linear combinations of probability measures, and that gave us examples of probability measures once more. But then we had also looked at another proposition which said that if you start off with a finite measure and scale it accordingly, divide it by the whole mass, then you also get a probability measure. But then this is about dividing by the whole mass, which is in some sense multiplying by a factor, correct? But this motivates us to look at this exercise, and this you can do for any measure. You don't have to restrict your attention to probability measures, but you can do it for any measures. So this is just a repeat of the earlier exercises that was done for the probability measures. So what is this? So if you have mu1 up, mu1, mu2 and so on be measures on a fixed measurable space omega f, then you have this set of exercises. First, look at two of them, mu1 and mu2. Then I say that I can add them up and get a measure. How? So mu1 plus mu2, that is defined as follows. So for any arbitrary set A, what you do, you add up the individual sizes according to mu1 and according to mu2. Add up the sizes, and I am saying that you will get a non-negative set function which is also countably additive. So all you have to follow are the earlier proofs or earlier methodologies that you have done for the exercises, and you will immediately get the countable additivity. By definition, this first example is of course non-negative because mu1 and mu2 both are known to be measures. So they will take non-negative values. So that's your first part. In the second part, I am saying instead of adding up two of them, look at the series. So now what will happen is that this series will give you a way of defining the series or summation of measures. What is this? So the countable sum of the measures is defined as follows. So for any set A, you look at this left hand side, and this is defined as adding up the individual sizes of the same set according to different measures mu n. So that gives you the second example or second part of the exercise. And the final exercise is that you can now scale it by appropriate scalars alpha. So choose any arbitrary alpha and choose this indices I from 1, 2, 3 and so on. Then if you multiply any one of the measures that was considered earlier, mu1, mu2, mu1, any measure that you have considered earlier, and multiply by alpha, you get a measure. So how it is defined? So alpha times mu y, so that associates the weight or the size to arbitrary set capital A according to this formula, that you first look at mu I of A, meaning you look at the size of the set A according to mu y, the measure given, and multiply it by alpha. But then this will be a non-negative set function because alpha is non-negative, and you can immediately prove the countable additivity exactly as discussed earlier. But then if you put them together, you are getting a non-negative set function which is countable additive, and this becomes a measure. So now these three-part exercises, what does it tell you? It says that you can multiply by positive scalars alpha and also look at additions. So therefore you can look at in general linear combinations of measures. So that is the takeaway from this exercise, that if you have some finite number of measures or a countable number of measures, then you can look at linear combinations or the corresponding countable sum of the measures, multiply by the appropriate positive scalars, you still end up with a measure. So this is a very interesting construction that will also allow you to construct measures in general from known examples mu1, mu2, mu and so on. So that is the takeaway from this exercise. We are going to stop here and we are going to continue the discussion in the next lecture.